We have Adam Buynak from Ohio State University at their Center for Design and Manufacturing Excellence, working in their Ames lab. He's the lead engineer.
All the energy.
It's not even midday yet. Within their group, where he's been doing a lot of development, mentoring students. They have a really interesting model about bringing in undergrads to participate and work on these projects and get them while they're young, or at least youngish, right? So, Adam, thank you for taking the time today. The floor is yours.
Cool. Hi. So, I'm excited to talk here today. My name is Adam Buynak, and I'm coming from Ohio State. Matt asked me to kind of give a little bit of a talk of what the experiences our team has had in ROS, a little bit of kind of what we've been doing over the past year. And Larry stole a little bit of my thunder, so I'll talk a little bit more about some of the projects he highlighted there through that. So we'll go ahead and kick off. It's just a rough overview of what I'm going to talk about today. So, but before we dive super deep into the kind of technical and the particular projects, I thought it might be helpful to introduce where I'm coming from and who am I as well behind that. So Ohio State University has a research center known for this as the Center for Design and Manufacturing Excellence. And our goal is to kind of function within the college, but still kind of outside of the traditional research lab structure in many ways. So our goal is to help companies, manufacturers, integrators take technology that was developed at universities and transition out into the real world. The way we enable that is our team is not faculty members. We're not out there and teaching classes. We're not doing many of the traditional day-to-day university activities. Our team is made up of many individuals who bring, 20, 30, 40 years of industry experience, and they're coming into the university and they're interested in helping teach students the knowledge they have and serve as really program management and engineering management to transition that technology out. So I'm rather young for being on our team. I'll highlight that. So anyways, what it makes up is a lot of individuals like myself who are actually kind of 30 full-time engineers and research staff. I think that number is actually a little old now. We've increased it since then. And our day-to-day engineering team is undergraduate students. So we employ over 150 undergraduate research assistants. My team in specific has about 11 students right now. We're slowly growing. And we also have, basically to go with that, as we have one foot in the kind of manufacturing world and industry, we have one foot in the research side of things as well. So through that, we have associated and affiliated faculty, grad students, your traditional PhD and postdoc, about 250 that kind of come across a diverse set of departments within the university. Through all this, we do operate a large ITAR and HIPAA compliant facility. So for the different areas that we fall within, we kind of focalize into about 7 different sections. So what we'll be talking about, where I come from, is our robotics and advanced automation organization. We also do a lot of work in metal additives. So if you think like America Makes, talking about other institutes that are out there. We also do a lot with kind of biomedical. So OSU's got a very large medical research. So think prosthetics, 3D printing, understanding how you can assist surgeons while they're operating inside. We've even looked at, like, for example, jaw plates, or kind of a plate that attaches up to your jaw while your jaw has been broken and getting repaired. Helping automated systems that can facilitate that surgery. So we'll click next. So the way we work, our goal is to kind of build on top of OSU's strong educational program and give students hands-on education, experiential education on site. So they're getting real-world manufacturing experience. They're working on industry-relevant projects. These aren't toy problems. These are things that manufacturers come to us or institutes have identified of saying that we need this technology developed. So our students gain the full experience going through that. Our goal is that students who leave our organization, again, these are undergraduates, can graduate and have effectively at least a few years of experience under their belt. Our offer back to the companies that are hiring these students, my goal is to place them in time, is that instead of a typical hire taking maybe a year, 2, 3, 4 that come up to speed with the technology they're working on, I think everyone's familiar with how long it takes to learn ROS. We can roll them out through even quicker instead of through internships. They've been working on this in the hours after class. They're doing it in between things. They're getting hands-on experience every day with this technology. And we're trying to bring them up to speed as well. It's not just the code that they're working on. They're involved with every step along the way. So students are working with me when I'm considering proposal writing. They're helping identify what is the project plan, laying it out, all the stakeholders, talking to our end users and understanding what their needs are. What does legal look like when you're talking about corporate interactions and anything like that? Then obviously all the day-to-day actual project execution. We encourage our students to fail fast, move quickly, try new techniques, move forward. There's a benefit of working within the university environment. We have that flexibility. We can do that for R&D. And then they're also learning regular personal skills. Everyone knows the kind of quirky CS student that comes out stereotypically. We help students break out of the mold, learn to be comfortable talking with end users, learn to be comfortable talking with people on the manufacturing floor. What are their problems? Help them come up with the solutions they have, mix in some other tech, and move forward from there. So that's our goal from a big picture. There's some of our students sitting with a Yaskawa system there in our lab. A nice glamour shot. So anyways, so our center's been around for a number of years. The group that I come from is the Artificially Intelligent Manufacturing Systems group, and we're newer. We've been around since just around before, or right before COVID kicked off. And it really came from a need seen across the industry, and we are especially starting to recognize it in Ohio, that there's a need for more artisan skills and advanced controls in robotics. And everyone's familiar with that. That's where a lot of the growth for ROS is coming from. So our goal is really to help address issues with increased production needs for low volume, high mix parts. Understanding how do we make it easier to program robots, because my maintenance technician is not going to go out and reprogram a robot on the manufacturing floor when there's a small tooling change. And basically addressing the workforce issues as well. All of that while maintaining safety and observability of the system. So that's who we are. That's an old picture. We got to get an updated one here soon. So we've got a lot more undergraduates that have jumped on our team recently. So far, over our kind of short existence here, we've worked a lot into the robotic blacksmithing kind of path planning type operations, primarily in the surface finishings as well as seam-based type operations. So think welding, dispensing, things like that. And one of this always particularly interesting is that communication back with the end user. So the operator is actually on the floor. What is their interaction with this automated system? How do they understand the decisions it's making, respond to them? And it's, at the end of the day, collaboration. So any team that doesn't talk with each other is a problem. And when your robot becomes a team member, you need to have a way for that robot to talk to everyone else in the room. So I want to talk about how we've taken some of those concepts into 2 different projects. And the first one I want to talk about is our drift project, as we like to call it, but is our robotic forging and incremental kind of process. So big picture thought here is we're talking about trying to take raw material, whether that be a billet or some kind of precast material. So you've kind of cast the part, and the desire is to eventually move into some well-constrained final shape that you can interact with. One of the big things we like to focus on is hybridized processes as well. So if I cast it and then I use a robot to kind of incrementally form it, so basically blacksmith it into another shape, I get really good strength properties from that process. And then maybe I do some machining to get good surface finishes in certain areas that are needed. So, we're combining processes. This is nothing new. The idea is how can we do this all within a well-constrained automated environment. So it is the modern day blacksmith. And so, anyways, one of the big things that we also keep in mind is on the research side of the house, how can you understand and control the material properties as you go through? So while we traditionally kind of do a lot of a lot of pre-planning, and the reason we pick our particular manufacturing process steps is we want to predict the material state as it moves through that process. One of the advantages of continuously having automated control on that is there's ways to integrate that directly into the control of the process and understand how it's behaving throughout and respond to that dynamically. So I've got a nice video. I like to show the glamour videos. So hopefully they'll start for me momentarily. Oh, there we go. Okay, so this is a demonstration we did back in December of 2023. So what we're going to see here is basically a robotic system putting in just a raw billet of material. This is just basically a carbon steel sewn in here and an induction heater bring it up to temperature. The goal is basically bring that material up to about 900 degrees C. And while it goes through this, it's going to heat it up. Well, it's going to scan it first, heat it up, and then it'll actually start forging it into shape. And eventually we're just going to cycle through this process over and over. The advantages of scanning the actual part is that we start to get an idea of the actual properties, the actual geometry it has. So the entire system, again, being very AI focused, is going to respond to the current shape that is set. So if you're starting with a raw billet of material or you're starting with a precast shape, you can make the appropriate motion plans that are going to correspond towards the final desired shape of that part. And I'll let us watch the video for a moment. So what we're seeing is kind of back and forth. We're getting even heat distribution through the part. The robot's coming over, setting it down in the press, and then it's slowly working to start make out some dies. So what we're going to see in the demo part right here is very simple. It's just a rod-like geometry. We're really trying to focus on just understanding how the material is flowing through this. Again, this technology is still in its early stages, but it's basically making a few initial hits, doing them evenly between. Obviously, we're sped up quite quickly here. And now it's working on slowly rounding out this part. It'll bring it back over into the heating system to kind of reheat that, rescan it, understand the shape it's taken, things like that. What's one of the really interesting things for us on this is, again, a classic kind of in-situation awareness. How do you actually measure and take a 3D scan of that part while it is at a high temperature? There are a lot of unique difficulties that come along with that, so we've been slowly kind of working through those different technologies. The part that you're working on here, so again, it looks kind of odd. It has no directly attached, manufactured part that we're going after right now. This is basically trying to understand how the shape, as you can control different geometries. So if we know we want to make a cylinder, or we know we want to make a square in that section, how's the material flowing through that, and you line up the appropriate decision making for that. To explain kind of what you're seeing as well, there's this big odd thing on the right side of the screen. This is a compliance device. So one of the challenges we identified is when you're working with a multi-ton hydraulic press, Rogers robots are not rated for multi-tons of force going back into them. I wish, but it's not yet there. That'd be a big robot. So anyways, what this device here is, handles compliance. So one of the challenges we highlighted, there's a need for the robot to set down the same as a human would and basically rest its arm down such that your left arm, if you're holding on to that part there, can basically kind of move and reflect to the parts and the forces that are being distributed onto the part there. Human blacksmiths do the exact same thing. Actually took us a second to realize that. If I'm holding the hammer, I'm going to hold my left arm loose, and I'm going to basically absorb all that additional shock coming back into the part. I think that's pretty much that. Yep. So that's how you get a robotic blacksmith. Just like baking. Add those three things together and you're good to go. Anyways, that's the final part. That was about an hour. So the neat thing is that before we did this, one of the parts that Larry had shown, we've been working with aluminum prior to this. This is steel now. So we were actually cold forming over multiple hours of work, just very small minor changes in aluminum. So adding heat into the process does allow the entire process to speed up significantly. So we've been really happy with the changes it's made. One of the other interesting things as well is you can have an automated system. It's doing its own decision making. When you're working with a, same as a regular blacksmith, you have other additional tooling and die selection in the part. So what you're seeing here is basically a squaring die. That's what was used in the entire video shown prior to this slide. And that squaring die gives you a lot of flexibility, but there's also needs for more punch-through dies, rounded edges, curves, things like that. So we've started also looking into like how do you make those decisions and teach a system to understand if I want this eventual desired geometry, what sort of die do I need to select? I've mentioned the reconstruction project, so also important to mention that we did have different project partners on this. So Capstan Robotics is known for their quality reconstructions and kind of pick selection capabilities. So we kind of partnered with them to use a Zivid system to kind of get a full structured light reconstruction of the part. And then we can basically load that in and get an understanding of what that part looks like and where to make the next hits on the system. One of the interesting things we found, and this is going back to kind of transparency of an AI system, is how do you embed a little bit of the human heuristic and guide it to making a good part, but also being able to qualify the process as it's going along. And one of the ways we've come up to address this is by actually taking your final geometry, comparing it to your initial start geometry. So the picture shown on screen here, we're just starting with a raw bill of material, so not actually a precast part. And you could basically say, if I want to start a little closer, so I'm not moving as much material, and maybe I'm imparting a different amount of, stress into the part, then I might want to cast about halfway along the process. So you can see the casting on the bottom left here is about the 30% mark, or about halfway up the item shown on the right side of the screen there. So you can start a little bit closer to your end goal, and that might change how the part actually behaves. And this is just another shot of the final parts there. So that was kind of forging. I want to highlight a second area we also worked on. This is another ARM project that was partnered with a few different folks, including Northrop Grumman, Yaskawa, and Aerobotics, but this is the painting system. So the big picture goal of this project was trying to create a smart way of coming up with path plans for parts that you can reliably determine where the robot needs to be placed over, consistent motion of the part to get a very even amount of coating of paint across the entire part. So We developed a few different technologies towards this that could be useful, deployed them in a system, and finally demonstrated them in 3 different test sites. So the system you see on the right side there is basically we're using no ether under the hood to actually identify where all the parts or waypoints need to move across the part. We ended up to do the paint simulation. There's a lot of great paint simulation code out there. The issue is you'll need a supercomputer to run it, or you need a really nice system. We ended up saying, well, why can't you just use this more simplistic model that gets you close enough? And there's a lot of other great tools that can basically collect those additional issues and help move it forward. It's kind of the reality to go through today. So we found some good luck with developing a GPU model that can actually use a geometric representation of the paint spray system. And that was quite successful for us. And this is also building on no ether. One of the things I'll highlight next here, as well as the user interaction, so transparency of a smart system back on to the user actually operating the scene. So, and this is talking about some of the demonstrations. I'll flip my slides around myself. So the augmented reality paint, so on the top right, you can see just 2 example parts there. They're just kind of generic test sheets, so kind of a flat one and then kind of unique geometry up on the part. These are, like I said, you can see they're nice raster-based processes. This is still using no ether under the hood to come up, so we're not totally walking randomly around on the part. That's not really optimal for a painting scene, and there's a reality of why today we use many raster-based processes. That's why if anyone asks you to go out paint by hand, you typically follow the same kind of concepts of the no ether system. So what we want to really shoot for is an AI that can kind of tune in all those parameters using the calibration settings that were fed into the system for how it's operating, the paint delivery is operating. And this is then using Tesseract under the hood as well for the motion planning. In regards to actually communicating, so sending back how the AI system is going to actually perform before you ever run the part, how do you trust what it's going to do, and making decisions along the way. We spent a lot of time considering how the human can work with the robot. So kind of calling back to the opening statements of this talk, one of the things that we want to highlight is how does the robot team member work with the humans in the environment. To me, that's something that's very important. If you have the argument that a human is never going to be involved in that process, I challenge you to reconsider that. Even if a human enters a robotic cell only 1% of the time that it's operating, that human is still collaborating with that system in some way. So understanding a way that the human can understand what the robot's doing when it's doing that or when they're just watching from the distance is quite critical. One of the ways we've tried to approach that is through augmented reality. So can you put on a HoloLens to device and actually interact with the environment, see where, in this case, the painting system, a heat map of how thick would the part be. So maybe you're going to see that maybe the path planner was not as good as you want it to be, or the motion planning couldn't reach certain areas of it, so had to make a compromise in certain areas. That's where our human intuition is really valuable, both for collecting that information to train the AI further and to basically make a real part today so we can get this technology out on the manufacturing floor. So it gives us a venue to basically perform that kind of communication. A lot of the work we found doing this is, find the experts who are in this area. So we didn't have mechanical engineers building this tool. I went out and found students who are game design students. So these are students who want to go out and build the next version of Call of Duty, as I always say. But I said, hey, there's this really cool manufacturing space. You have a lot of valuable skills. I think you're going to enjoy this. So I had a few of them that took a risk and came out and worked with us in the kind of manufacturing-focused products, and really enjoyed and kind of learned to value saying, wow, I've never considered these other fields as something I could work on. So CDME really wants to focus on helping students identify other areas they can work on and recruit those necessary skill sets into our industry. And they can build some really cool tool sets. So as you can see on the top right, kind of this fancy scroll menu that allows the user to interact with the scene, and as well as these kind of 2D menus. One of the things that we found really valuable is kind of tying back to what does the end user actually need. We took this technology, and Northrop actually went out on the floor with their operators who are using this and say, what are the useful parts of this tech? What was the bad part? What worked well? What kind of interaction of the menu worked well for them? And so the little cool menu on the top right has a little kind of GUI and graphics. I personally thought it was okay. My students loved it because this is really neat. We went out to talk to our operators to saying, this is a little too fancy at the end of the day. It works well, it looks nice, but it's not that useful for me. And so we got rid of it. Said, okay, this doesn't make sense. So let's go back to just a 2D menu and try that out. Everyone's happy with that. Everyone knows how to use a 2D menu. But we found good ways to make it interactive. So you can kind of resize it, pull it around things that are more naturally to interact with. You might look a little silly to someone who's not wearing that HoloLens and seeing you interact with that environment, but it's a much more natural process. So we can actually show that data. We're doing local registration to show basically 2D or 3D visualizations overlapping with the real world parts and interacting with the scene. And for anyone who's worked with HoloLens, we are using the TCP endpoint. I always get asked that question, so I wanted to make sure I threw that up there. And then we also felt it was useful to do in RViz. So one of the useful things is build out a UX environment. You do have to keep in mind how you're going to maintain that system, allow the tools that are under the hood, the advanced settings, if you may, for your developers to continue interacting with it. And so using some of the inspiration from the Scan and Plan workshop and then kind of mixing in some of our own flavor on top of it, we built a lot of tools that allow you to interact with the scene, kind of do almost painting. So if you think of kind of the Microsoft Paint tool, go in, select surfaces on the part that you want to paint with, and that'll can feed into the rest of the system as well. And you can visualize everything on there. One of the things that we found really interesting as well is a lot of behavior trees and state machines that kind of Michael highlighted this morning is the developers, or let's say students who are really kind of digging in, trying a lot of code issues, or when you're doing the development phase, things shut down and break randomly. So we really wanted to prioritize setting up some clear visualization of what nodes are still alive, what is their status, almost as, and I think of it in my mind, of when you go up to the kind of large control panel on a manufacturing system, where are all your indicator lights? Is like it flashing? Is there a problem? Is it still safe to operate, but is there an issue going on under the hood that we can keep on running it, but we need to give it some attention to it? So trying to show these views. And for my final slide, just as an interesting development note, the way we approach this is that to reduce all the computation, not so much mattering for RViz, but especially for Unity and the HoloLens environment, to try to maintain as much of a streamlined interface for the user. There's no lag for them interacting. We kind of offloaded all the actual computation required for the user to interact with the scene, the controls, into basically this back-end kind of user experience server. And then that's where Unity and RViz actually pull all their data from. So that way it was nice that we could actually, for development purposes, stand up all the actual controls, show something without needing the entire state machine and all the actual plans. So we can basically load up existing plans, interact with them, show them off, demo them, things like that. And that's a great way for us to actually show this technology to people on the floor and understand how it will interact, what their needs are, without bringing all the other luggage of the decision-making tools on the back end. So I think that's my final slide. So again, my name's Adam. We do fun, oh, I clicked a button. We do fun things like pumpkin carving as well. I like to throw that up there instead of a picture of me. You can just see me here. So our students come up with all kinds of clever, fun stuff to do, and that's one thing that they seem to like doing every year now. So, but that's what I got. Thank you for listening, and I maybe have a question if you want. Oh, thank you.
All right, thanks, Adam. Adam has time for questions. Are there questions in the? Oh, look at the hand.
Oh, boy.
We'll start with Corey. She's closest to her front.
Do you have any, does the university or you as a person have responsibility for publication, and how do you manage that?
Yeah, good question. So the question was, you know, the way we operate, are we required to publish? Do we hold anything like that? The direct answer is no. So I have no, specification to say I need to go put out so many papers or things like that. Our goal is for, again, like I mentioned, we kind of have 2 feet in the world, one in the more manufacturing focused and one that's more in the research side of the house. So for example, the paint project, some of the things I didn't show is that we also spent a lot of time looking at like the more futuristic AI planning for surface processing and things like that. We are actively looking at getting that into a research paper so that can go out into the other like-minded individuals who are trying to push that advanced algorithm development. But we're trying to also take a lot of the code that we've done and put it out there for people who need the more practical, this is ready to use today technology. So it's something we like to do when we have something that is worthy to go into the conferences and papers and stuff like that. But there's other stuff that it doesn't make sense to publish on. It's more of a practical deployment. So
thanks. Omar, do you still have a question?
It's a great question. So the question was, how do we actually account for basically the fact that you're scanning a hot part? And so if you have a lot of IR radiation going off on that part, you can get different artifacts on the scene and things like that. It's a real challenge, and I'll say that I don't have the perfect solution for it yet. We found different clever ways of, as you notice, I basically do my scan after I've forged the part. So the temperature on the external surface is much cooler than the center core temp. So if I put it in the induction heater, it can come right back up the temp on the outer side much more. So we found that makes it easier for us to scan. One of the things we found is we've been using structured light. So there are advantages in structured light, again, different light spectrums on where your select sensor is collecting that data. Of all things, we found scanning it from different angles helps out great. So basically structured light is obviously using a banded type approach. Doing that at different angles, even though your sensor might be still taking in any spurious data into that, you can basically overlap a lot of the information and kind of get a more robust scan. So at the end of the day, more scans, clean up your data a little bit more. So no perfect solution yet for cleaning up hot work.
Learn by doing.
Yeah.
Right? We love the Vivid camera too, right?
Yeah.
Cool. Any other questions for Adam? I guess I have a question, right? You talked about bringing undergrads in, and you guys are doing, like, poking at ROS stuff, a lot of ROS development here. Can you share a little bit about your experiences exposing undergrads to ROS and some of the things, tricks you've done to kind of make it more approachable for undergrads? Yeah, absolutely. It's an interesting challenge too. So over our short time, we've brought a lot of different undergraduates in to learn the basics of ROS. The first thing and most important is I don't want to always reteach, so we try to identify the resources that are out there already. The first challenge is usually just trying to get people onto a system that they can get in and start poking around at things. So I've always been a big fan of the scan and plan workshops because it is a working function that they can pull onto their system, assuming they can build it, and get everything there and figure out how all those parts are working. So that was step one. That's very valuable. Step two, believe it or not, is getting students familiar with the Linux system. There are many universities that are primarily focused on Windows and just getting them up comfortable working with a terminal and things like that. So it's almost these little barriers of getting them past, of getting comfortable with Linux, one we run into every day. Yeah, GitHub, of course. We have a huge priority on teaching students proper code management, version control, unit tests, maintainability of the entire system. It does slow us down from a research perspective, but it's invaluable to the student's outcome at the end of the day. So, and for us, as we've been slowly growing, my students that have been here for longer over time have been great at helping us maintain that level of acceptable development. So new students are onboarding faster and faster every year.